To get the webinar started, here is Paratherm Global Director of Technology, Ryan Ritz. Ryan?
Thank you very much, Molly. Hello, everybody, and thank you for attending today's presentation. As Molly said, my name is Ryan Ritz, and I am the Global Director of Technology at Paratherm Heat Transfer Fluids, division of the Lubrizol Corporation. So today, the topic that we are going to be presenting is on thermal fluid hacks, which are basically just quick tips to elevate the heat transfer operations in your thermal fluid heating system. So to go through, anyone that spends even a relatively low amount of time on the internet or on social media sites has most likely come across a variation of a life hacks list along the way somewhere. These lists provide quick and easy tips to apply, tricks for making everyday tasks more convenient. And in the spirit of these lists, this presentation is going to aim to provide a similarly useful and easy to apply list of tips focused on improving the user experience for heat transfer systems. So to go forward with that, you're familiar with these lists that you've seen, 30 amazing life hacks that would change the way you live. And basically what they are is just kind of neat little tricks and tips that you can take what you already have existing in your environment, make a quick application to them, or possibly knowing something, an insider trick that most people don't know to be able to improve your user experience. For example, making a speaker out of a cardboard tube and some thumbtacks for your cell phone, or using grapes instead of ice cubes, frozen grapes that show your lifeline. Just little things that might be obvious after you know them, but once you do, they can make things a lot easier and a lot more convenient for you. So in that spirit, we're going to be providing just a quick hitter overviews of some inside tips and tricks. Probably best to be applied for we're not going to be giving much background on general heat transfer fluid systems or thermal fluid systems, but some insider information that you can get and easily apply in your plant. So thermal fluid hacks, taking a play off that life hacks list. So defining the scope is how we're going to start off. And what we mean by that is just giving you an overview and a background of what heat transfer fluids are quickly, and really the technologies and chemistries that we're going to be addressing throughout the rest of this presentation. So glancing ahead into what you're going to see on our version of the life hacks or thermal fluid hacks list, you're going to learn about quick and easy ways to make sure that the very first decision you make in your operation for a thermal fluid system, which is choosing the proper fluid, critical and early step, giving you some really easy but critical things to look for when you're making those selections. Next, we're going to be talking about some contamination issues. There's water in your system, moisture, which there always will be. Some easy ways to notice that happening and how to take care of that and remove the water before it becomes a serious operating and safety hazard. In light of that, we'll also be discussing some tips and tricks on fluid changeouts, the proper way to do that. It's something that's done incorrectly a lot of times, and just by changing out the fluid or charging the system or draining the system, you can give yourself a lot more of a headache, maintenance-wise and operating-wise, than you need to. Going over some tips on preventing degradation, being able to recognize the signs that your fluid's breaking down and how to prevent those from happening. Key point behind that is going to be the proper operation of your system, especially on startup and shutdown. So we'll review those steps and some advice on how to properly start up and shut down the system. Really easy and obvious things that you may be overlooking every day on the sounds and sights and readings that your system is putting out on system monitoring, and what those could mean long term. Some things you probably aren't keeping tabs on but probably should be. So that's going to be some hacks on system monitoring. How to avoid contamination, really getting a little bit deeper into what flash point actually means and defining it so that safety managers and maintenance managers can really understand what that means and how to apply it to your actual thermal fluid heating system. And then one of the things that brings these all together and is probably the best and most useful and most highly recommended thermal fluid hack is going to be maintaining a proper fluid analysis program. and then we're going to get into wrapping the entire thing up. So without further ado, our version of the list of life hacks or thermal fluid hacks. Starting off with the scope, what do we mean by thermal fluids or heat transfer fluids? Well, you've heard me say that interchangeably by now at least a few times. So heat transfer fluids are also known as thermal fluids or thermal oils, heating or cooling fluids, or hot oils. Key point behind these products and this technology is they're able to generate relatively or very high temperatures, but also maintaining low system pressures. So you can obviously tell with high temperatures of steam systems or direct heating, you obviously have a lot of problems that can arise from high pressure areas, hot points, direct heated areas. So thermal fluid systems, heat transfer systems are designed to be able to give you the same temperature ranges but maintain lower system pressures for better maintenance criteria and better long-term operation of the system. They offer safety, low maintenance, extended operating lifetimes. They're also highly efficient. They're non-corrosive, so non-aqueous is what we're really going to be focusing on today, and allow for accurate temperature regulation and uniformity across the entire heated area. So this presentation scope is going to focus on just that, high temperature thermal fluid heating systems and the fluids themselves. And we're not going to be talking much about aqueous or water-based glycol type systems. So we're going to be focusing on non-aqueous, natural and synthetic organic hydrocarbons, these based heat transfer fluids in closed loop circulation applications. Okay. So there's a quick chart here to show you what we mean on the temperature scale. Heat transfer fluids, this bottom area, aqueous fluids, glycols and brines. While some of the tips that we're talking about may apply to those systems in general on a broad-based scale, we're really going to be more useful for systems operating a mineral oil-based product or a synthetic aromatic-based product. That's really what we're going to be focusing on. They break down different, the elements are different in the systems, the compatibility of the materials of construction are different. So we're really going to be focusing on more oil-based, hydrocarbon-based products. So our first fluid hack that we're going to be talking about, and it's titled here, Make the Right Choices. And this is the upfront decision-making that takes place when applying a new heat transfer fluid, a new thermal fluid to a heating operation. It's extremely important to know what you're looking for in making your fluid choice. So some really quick things that you should be looking at. Your operating temperature range is extremely important. And we're defining maximum operating temperature and minimum operating temperature. And the key point that you want to take forward with this fluid hack is that your maximum operating temperature should be what your actual process is drawing for. So the outlet temperature of your heater is going to be at a temperature that allows your heated process to be able to be at its design temperature. So it's not going to be, when you're looking for a fluid, you have set points on your heater and a maximum allowable set point that the heater can actually achieve. What you're more interested in is going to be what your process is actually calling for. That's the discussion you want to have with the potential fluid suppliers. And one of the key points of what you need to look for is making sure that that maximum operating temperature that you are physically operating at or planning to operate at, you have a nice cushion between what the maximum operating recommended temperature of the fluid you choose is going to be. Because remember, when your system is kicking in and out of high fire, or when you're starting up, or if somebody makes an error in the set point, or you decide to maybe increase the temperature to get a different output, you could be approaching limits of that fluid that are going to cut the life of the fluid in half, maybe 3 times the rate of degradation, depending on how much that increase is. So you want to make sure you have a nice cushion between whatever the maximum operating temperature recommended for the fluid is and what you're actually going to be operating at. So that's a key point there. Minimum startup temperature, if you're operating in a cold weather environment, you want to make sure that you have a fluid that's rated to be able to start up and efficiently transfer heat at the temperature, or efficiently be able to move through your system and pull the heat from the heater at the temperature where you're going to be starting up. So take all those things into consideration. Just don't buy a fluid because it says it's a good heat transfer fluid and able to meet certain temperatures. So other levels of other considerations that you're looking at, levels of impurity. This is an extremely important one. Keep in mind that these fluids do break down over time no matter what when they're exposed to high temperatures. But a fluid that has a lot of impurities inherently in it when you start off from brand new state are going to break down a lot faster because those impurities will foul out. We're talking about impurities from natural hydrocarbon process. So you're looking at asphaltene, sulfur-based fluid, sulfur-based impurities. Taking a look at the picture that we have here, a really quick, good way to look to see if you have a proper heat transfer fluid for your system is by checking out the color of it. You want to have something, when you're talking about the natural mineral oil-based products, you want to have a fluid that's going to start off with a very high purity level. And that's not just for toxicity issues, but the big issue with that is going to be you don't want to start off with impurities in your system right off the bat that are going to foul out onto your system and cause all kinds of operating problems down the road. So starting off on the right foot is important. Keep in mind also that a lot of the synthetic aromatic type products will have a light yellow inherent color to them. Those synthetic chemistries do have that inherently. So know what you're talking about, know when to apply the color theory, stay away from anything dark brown or amber or orange or dark deep yellow as a good rule of thumb when we're talking about fluids in general. So yeah, that's the proper fluid selection. Key point, right off the bat, can make a huge difference in the entire life of the equipment and the fluid just by making that one choice. So do your homework, look into things, make sure that all these criteria are checked off. Performance capabilities beyond that. You want to make sure that you're having a discussion with a thermal fluid supplier that can provide you with the advantages of your fluid, not just based on what the additive package might be or what their temperature range might be, but you really want to have them be able to discuss with you the advantages that their product offers in terms of the thermal stability, which is the ability of the fluid to handle high temperatures over a long period of time without degrading quicker than something else relative to it. So thermal stability is a test that should be able to be provided to you or discussed at least based on the chemistry of the fluid that you're using. You also want to make sure that another performance criteria, heat transfer efficiency, and that's something that can be calculated based on the system specifications that you have, your flow rate, your pump size, your pipe diameter, the temperature that you're going to be operating at, and all the fluid properties and characteristics that are going to be at that temperature of your operation can be used to calculate what we call the inside film coefficient. That property can then be compared to other fluid at the same operating conditions and compared to see which fluid will be better at pulling that heat away from the film layer of the piping and give you better, more efficient heat transfer over time. We already discussed product purity when checking your fluid sample, and again, you're a fluid supplier. That part of that conversation needs to be performance capability of how purified is this product. Show me documentation, show me some kind of proof, send a sample that you can see the color, have that discussion to balance those primary factors. Some secondary features to be considered, and I would not prioritize any of these really over those top three, but still some things that have been considered and talked about. But again, I consider these ancillary features secondary to the main ones above. So the expansion rate of the fluid, that's really for sizing of your valve, sizing of your expansion tank. What's the flash and fire point? That's more of a storage issue, and we have an entire thermal fluid hack dedicated to flash and fire point later on. Oxidation resistance is another one. If you have a system that inherently is going to be a problem area for oxidation, you can discuss that with your manufacturer as well. Your startup temperature based on your environment, vapor pressure, and obviously cost versus performance. A supplier can offer you what they say is the best fluid that will last you for 100 years, but if it's not within your budget, then it's not going to meet your needs, no matter what the performance criteria are. These are all things that you should be checking and making sure that you check off the list when you're talking to your fluid supplier. They all too often get overlooked, and most of the time, reputable fluid suppliers are offering this information without being asked. So I think it needs to be, it's a good idea to have the user and the potential user have this checklist to be able to ask when they're looking for fluids to go off that. Okay, so our next fluid hack, time for a change. And what this one is going to be addressing is what you need to look for when you are either introducing a new fluid into the system or you are changing an old fluid that has broken down, or you're going through a maintenance interval, You need to top off maybe. So this is all things that you really need to look for, some insider tips on what to do when you're changing fluids out. So proper fluid change out, draining systems. Key point when you're draining a system, make sure you have the fluid analyzed by either the manufacturer of that fluid, if they offer that kind of a program, or a reputable lab that specializes in thermal fluid analysis. You really want to make sure that if you're draining a system out anyway and going through that maintenance procedure, what is the condition of the fluid? What is the condition of the system going to look like after you drain that system? Okay, so if you need to have flushing or cleaning step, fluid analysis will help you determine if you need to go forward with that. It might even stop you from draining a system that doesn't need to be drained. You might think, just based off of the fact that it's been in there for a certain amount of years, that it needs to be drained out. A fluid analysis could possibly save you some time and money on not having to do that. So if you do have a fluid analysis that determines that there's probably sludge buildup or solid particulate buildup in the system, you're going to want to keep that fluid as hot as possible while still maintaining a safe operation when you drain it out. And the reason being is a hot fluid will be more active and more turbulent in flow. It will have more solids suspended. The fluid will be thinned out more when it's hot. So when draining that system out, you'll get a more complete system drain when you have it heated up. But again, you want to make sure that it's safe enough to operate with your people and with whatever equipment you're using to drain it. Also, you want to run the draining process out until you hear the pump cavitate, making sure that you have valves, high point valves open so that air can get in and kind of you're not pulling a vacuum on the system. But you want to make sure that you have proper flow and complete drainage of the system to get all contaminants and most of the fluid out that you possibly can. And keep in mind, when you're draining a system, rule of thumb, there's likely going to be, at best, with you do a really thorough job of draining, around 10 to 15% of the old fluid left. So keep that in mind when you're draining a system. It's never going to be a perfect drain. You can get a vacuum pump or anything else, but you're still always going to have system contamination. So keep that in mind. And know the condition of the fluid is extremely important so that you know how thorough your change-out actually needs to be. The worst thing you can do is invest in brand new thermal fluid, heat transfer fluid, and you went out and followed the first thermal fluid hack, bought a good quality fluid without a lot of impurities in it, and you did all the right things, and you go and you fill the system up, and you've got 20% of your old fluid with sludge and contaminants and solids left in there, and you just contaminate the fluid right off the bat. So that's an important step to take when you're draining your system. Get the fluid analyzed beforehand and do a thorough and complete change-out. When you're charging a system, now this is either a new fluid charge or if you're charging a system with existing fluid in it. Avoid filling the system from a high point. So a lot of times we'll see users try to fill the system from the expansion tank because it's an open, easy to access area a lot of times where they can just pour drums of fluid or set up a hose in there and just start filling from the top. What you end up doing when you fill from the top is you're actually pushing air and any moisture buildup or any contaminant buildup that has settled out in the expansion tank, you're actually pushing that down into the system from the top. And what we're aiming to do when we're charging a new system is to push all of the air and everything else out from the bottom up through the high point drains or high point valves as the system is filling up. One of the most difficult things to do on starting up a new system after it's been charged is to remove air from that system when it's already filled. So you get the system filled up, you've got air pockets throughout the system, you're going to cause all kinds of startup and operating problems until you remove that air. Filling from the bottom will push the air that's in the system inherently up out of the system through the expansion tank and any high point vents. So try to fill up through the bottom, and by doing that, you can use the main pump, throttle the block valve on that main pump discharge for a cold circulation. Or you can, if you have a gear pump, you can cycle that on and off. That'll prevent pump damage when you use the main pump to fill the system. You can add fluid when the pump cavitates and slowly increase the flow rate until the entire system is full. Make sure you fill all the loops. You can isolate loops and do them one at a time. But you want to make sure those high point vents are open and have somebody there at the high point vents with a bucket or a container. As the fluid reaches each vent in series, it will push the air from the vent. You can close it down when the fluid reaches it, and it will move on to the next one. Now you have the proper fluid. You've drained out the old fluid that was in there. You've made sure that you've got it all out and it wasn't anything that was going to be really bad. Now it's time to start your heater up. Okay? Important point, and we're going to focus again on another hack later on in the presentation on startup and shutdown, but heater startup is extremely important. You want to make sure that you increase the system temperature slowly. Take control of that so that you don't, A, overheat and crack the fluid from startup, and B, you don't have any inherent moisture that might be built up in that system, doesn't flash off as a flash steam problem. That can create a situation where the fluid actually gets violently discharged out of the top of the expansion tanker vents. So you want to make sure that you're slowly heating the temperature up to between 210 Fahrenheit to 250 Fahrenheit. And it's no coincidence that's right around the boiling point of the water that might be in the system, because you want to slowly steam off any water that's there instead of flashing it off. Pump cavitation and expansion tank, we call them geysers or violent discharges from the tank. That will mean that there's water in your system. And the only way to completely remove that water is to flash it to the atmosphere, slowly steam it off. So when your system is dry, you've got all the water out, the pump is stable and not cavitating anymore, you can increase the temperature up above 250 at a higher rate. When we're talking about draining or changing out systems, charging new systems, we're always worried about compatibility concerns. Now, that's compatibility with materials of construction. You want to make sure that your thermal fluid supplier can offer you a compatibility list of all common polymers that could be used in your seals and gaskets. That's extremely important. Make sure you actually have the system built up to begin with while it's empty, so you don't have to do that as a maintenance area activity later on. What's even more common of a problem with changing out systems with compatibility concerns is contamination from old fluid or mixing two fluids that are of incompatible chemistries together. So fluid-fluid compatibility is extremely important to consider as well. So when you have existing fluid replacements, test it. Fluid analysis. This is going to be a recurring theme throughout all of these life hacks, and it's going to be a hack itself. Fluid analysis is extremely important here. You want to make sure that miscibility, reactivity, contamination issues with the old fluid and the new fluid are not going to become a problem for you. Never introduce water into a system that you're going to be using oil-based or synthetic aromatic hydrocarbon-based heat transfer fluid. They are incompatible, and you'll cause yourself all kinds of problems. Somebody says, why would I want to put water in my system, or how would that happen anyway? Well, there are a lot of services out there that offer professional cleaning or steam cleaning of these systems that are using a water-based aqueous cleaner. So you would be surprised at how often we face those kinds of issues. But we always say, make sure if you have this kind of professional service done, they are not using any water-based type cleaners. It's going to create a serious issue for operation down the road. On that note, we bring ourselves to our third thermal fluid hack, which is say no to H2O. Water is a very special case when we're talking about contaminants because it's probably the one that causes the most headaches in plant operation, startup, and if you have a seasonal operation especially. Whenever you start a new system up, whenever you add fluid to a system, you're likely to introduce even possibly relatively a small amount of moisture to it. How is that possible? Well, drums left outside for extended periods, they have water pulled on, rainwater that gets pulled up on top of the drum itself, and as the temperatures fluctuate in the environment, you could possibly pull a vacuum inside that drum and pull some of that water from the top of the drum into the fluid itself. You could possibly have transfer pumps that you use to fill the system laying around that have moisture in them. Any offline equipment is likely to have moisture built up into it. New system components, piping, pumps, any vessels that you have could possibly have rainwater or moisture from a humid area built up in them. So, when you're thinking about those types of situations, it doesn't seem like a lot of water would be there as a problem, but just a good visual kind of idea, visual example of this is take a 12-ounce bottle of water or can and know that much water, when it's actually heated rapidly and flashes into saturated steam, will actually displace about 55 gallons worth of volume in your system itself. So that's got to go somewhere, and if you're heating up rapidly, that amount of moisture will go out the top of the expansion tank in the form of hot transfer fluid raining down on the plant and potentially personnel that are around the area. So very important to make sure that you're aware of any water that's in the system. Take it slowly. Listen for the pumps cavitating. That's kind of worst case scenario. If you have moisture, best case scenario is you're going to have some serious issues with pressure fluctuations and pump cavitations. Inherently, heat transfer fluids that are non-aqueous are just that. They should not have a high amount of water in them. We're talking about extremely low ppm values, if anything, and that should be indicated on the quality control report that should be on the certificate of analysis from your supplier. The things to look out for to make sure that you're getting a quality product. So we already discussed this: pressure fluctuations, hot fluid discharges, and serious damage to your equipment. Pump impeller pitting, your expansion tank could rust out from the bottom. If you have these violent discharges of fluid from the tank itself, it could come in the form of the actual expansion tank falling to its side or violently jumping up into the air when you have these kind of problems happen. So a boil-out procedure is very time-consuming. I highly recommend going through your thermal fluid supplier and your equipment supplier for tips and techniques on how to boil out the water. But basically, you need to slowly steam it off out of the expansion tank, keeping the expansion tank warm so that the fluid is removed properly without condensing back into the top of the tank itself. Our next fluid hack, number 4, danger, flashpoint. And this is in bold, capitalized letters with exclamation points for a reason. A lot of times we get some very panicked calls when the fluid shows up and someone realizes that the flash point may be below what their actual operating temperature is. A safety manager gets wind of that and says that it's not supposed to be used at that point. This is the statement that we hear a lot: my heater outlet temperature is higher than the flash point of the fluid. Am I going to have a fire? At this point, we like to tell everybody, please just slow down. Let's have a discussion, and we'll educate you on what flash point actually means. So you guys get the benefit of having that done now through this thermal fluid hack. Flash point is actually mostly going to be used when we're talking about these types of products and systems. For transportation and shipping regulations, they need to know how to placate the trucks, and for storage regulations, to know what kind of fire suppression systems you need to have in place or what kind of signage you need to have on your building. But in terms of actual operating heat transfer fluids, flashpoint is something that is a minor, relatively minor issue when you're looking at the actual operating temperature specifications. And the reason being is flashpoint is actually defined as the minimum temperature of your liquid at which sufficient, and these are underlined for a reason, sufficient vapor is given off to form an ignitable mixture with the air near the surface of the liquid in the presence of an ignition source. So those 3 things are all necessary for a flashpoint to become relevant. You have to have a high concentration of vapor formed at the top surface of your fluid. That needs to be mixed with a steady stream of fresh oxygen near that surface, mixing in with the fluid vapor. And then you need to have an ignition source, so a spark, a flame, possibly red hot metal is what people always call into play when they're questioning the validity of this. But the key point is, when you're talking about a closed loop heat transfer system, those 3 elements, those 3 ingredients to create a flashpoint issue, to where that actual physical number, that characteristics comes into play, are virtually impossible unless something very bad happens that we're talking about a catastrophic failure to where you have significant failures all in series, cracked heater tube maybe sprays fluid into the flame of the heater box. Maybe a violent discharge of fluid from your expansion tank that goes directly down your exhaust stack into your heater. And honestly, at that point, forget about whatever the flashpoint value is. That gets thrown out of the window. Any standard fluid will ignite under those catastrophic conditions. So leave those flashpoint worries to the warehouse managers and the shipping coordinators. Direct the focus on selecting a fluid with properties that have actual relevant impact to your system. Okay? So thermal fluid hack number 5, we call this one Smooth Operator. And the topic that we're going to be looking at here is really kind of the basics of system operation that also, even though they're fundamental, they're done incorrectly more oftentimes than anything else. When the system's at steady state operating, it's doing what it's designed to do most of the time. But at startup and shutdown, operators usually make the most mistakes that has the most detrimental final effects on the fluid in terms of premature degradation. So this hack is really supposed to give you insight on the tips and tricks, and not even tricks, just the proper way in a quick, concise language on how you should be starting your system up when you're starting it up from ambient up to the actual operating temperature, and how you should be starting your system down. So the key point here is when you're starting a system up, the fluid is going to be at ambient temperature. It's going to be cool. It's going to be more viscous than it is supposed to be designed to be at your operating temperatures. When fluids are more viscous, they're not flowing at the proper rate. You don't have that good turbulent flow that you need for efficient heat transfer. So at that state, if you have any quick concentrated temperature rises, that high energy output that's being applied to the fluid, you're actually going to be cracking the fluid molecules right at that heated surface. What happens when you do that is the fluid actually will foul out onto the surface of your pipe or whatever your heated surface is going to be. So you want to make sure that when you're starting a system up, you start up slowly, because knowing that fluid is going to be more viscous, it's not flowing the way it should be, it's not pulling the energy out of your system, you don't want to shock it with extremely high flux of energy all at once. So start up slow to keep the fluid protected until high fire goes on. You want to make sure your viscosity actually drops down below around 10 centipoise. Why 10 centipoise? At that point, typically, rule of thumb, and remember these are all kind of generalizations when we're talking about these things, as hacks usually are, but when your fluid reaches around 10 centipoise, most fluids that are actually legitimate heat transfer fluids at that point are at a viscosity level where they can actually reach turbulent flow in most legitimate systems and pull the heat out without damaging the fluid. So you want to make sure you look at look towards your fluid representative, your fluid supplier, and ask them when this point is going to be, at which temperature you're going to be looking at. It's usually between around 180 to 200 degrees Fahrenheit. So you don't want to let your system kick onto high fire before your fluid is uniformly at that temperature. Okay, so once that turbulent flow is reached, you can raise your set points at much larger increments. So you want to start up slowly, 10 degrees at a time, ramp it up slowly until you get to that 180, 200 degrees, wherever your fluid viscosity is proper. Then you can actually start increasing to higher temperature intervals after that point. If you do not do this and you let your system kick into high fire, or you put an extremely high ramp-up temperature, you set it at its maximum right away, you will do irreversible damage to the fluid, and not only that, irreversible damage to the surface of your heating elements, whether it be the pipe or electrically heated element or heat exchanger, whatever you might be looking at. So it's a very expensive mistake, and it's a very easy mistake to be able to avoid. Just take some patience and some know-how on how to do that. On part 2 of this hack, we're talking about system shutdown, and this is even more of a danger when you do it improperly. When you turn off your circulating pump while you're at your actual operating temperature, you turn your system off in its entirety, so your pump goes off at the same time as your heater, that will actually result in raising the temperature above the maximum bulk temperature of the fluid itself. So what you're looking at is you're looking inside of the heater chamber. Even though you've turned that heat source off, because the fluid is not circulating through the chamber, it's just sitting there stagnant, the fluid temperature will actually rise because it's in an insulated environment and it's not flowing to be able to pull heat out of that environment. So that energy, that heat energy, you're basically creating an oven at which you're baking the fluid itself. It'd be akin to taking a pan of olive oil, and instead of putting it on the surface of your stove and stirring it continuously so it doesn't burn, You just put that inside of an oven that was preheated to 500 degrees and let it sit there. It's going to burn and crack and cause all kinds of serious issues within your heater tubes, which are the most vulnerable areas for degradation anyway. So, key point for this hack, always keep your main circulating pump in full operation when your heater is powered down. Let that fluid flow through the heater and pull all of that residual heat out of it before you shut the pump down. When you reach around 200 degrees Fahrenheit, then you can shut your pump off. Now remember, this is when you're shutting the system down to do some kind of maintenance, or if you're just not operating over weekends or an extended period of time, you want to do this. Another insider tip, though, is that if you do shut down on weekends and you're not operating, you're probably going to save a lot more energy by keeping the pump and the heater on at very low rates. It's much less energy to start a system up and ramp the temperature back up versus the alternative, which is if you go from a complete shutdown where you've gone all the way back down to ambient. So that's up to your user criteria. But that being said, regardless, do not shut the entire system down all at once. Always make sure you keep your circulating pump running after you turn the heater off until you cool it down to around 200 degrees Fahrenheit. Okay, brings us to thermal fluid hack number 6, which is titled Keeping Tabs. And this hack is going to be focused on periodic physical monitoring of your system. This is kind of the one hack on the list that is not going to be found really in a manual or literature, but it's more just good maintenance practices, what to look for, knowing your system, how to listen for different things, what to look for under normal operations, what your gauges are supposed to be at versus what they might be at off on an off day. Knowing everybody that is going to be responsible for the system, understanding what the set points are supposed to be, what the operating conditions are supposed to be, and really taking ownership of those things and understanding them and being able to notice when something's not right. So knowing the system, walk the system, take a look around, listen for it. If you're hearing crackling in your expansion tank or popping, and that's not a normal thing, that's something you should monitor, because likely you have a situation where you have moisture and water in your system that's starting to bubble and boil into the expansion tank itself. Differential pressures going through the heater themselves. Your maintenance staff, your operating staff should know what those differential pressure across the heaters is. And if there's any change in that, if you don't have an automatic alarm or automatic kill switch that's going to shut the heater down when the differential pressures are out of whack, you need to have guys that know what they're supposed to be and monitor the changes for them. Another really good hack is to be able to kind of get a rough estimation or a rough idea of the efficiency of your heater over a long period of time. When you first commission your heater or when you make a fluid change out, take note if you have a reading on what the waste heat exhaust stack coming out of your heater actually is. Note the temperature of that. Basically what that's an indication of is, you've got a flame going down that's supposed to be putting energy into your fluid. That energy is supposed to be used up in a system. Whatever temperature, whatever is of the exhaust air that's coming out of the top, that's actually considered wasted heat. It's inefficiency in the heat that's not going into the fluid but going out into the atmosphere. And that's fine. There's no such thing as a perfect heating system that's going to be 100% efficient. So what we're looking for is changes in that efficiency. So your normal exhaust stack temperature, all other things equal, should remain relatively consistent over time. And if you start to see that exhaust stack temperature raising higher than what it was when you first commissioned the system, that's a good indication that now that energy that used to go in your fluid is now going out into the atmosphere instead of that. So what's the problem with that? Well, why is it not going into your fluid? That's something you really need to question and look at. It could be possibly one of two things. The fluid's degraded so bad that it's not efficiently pulling the heat out. You've got fouling on the inside of your heater tubes due to the degradation. That's actually creating an insulation layer between the heat energy and the fluid. Or probably the best case scenario is, depending on what kind of fuel you're using to heat your system, you could possibly have soot buildup on the outside of your heater coils. That's a much easier one to fix. You just blow out the soot from the coils, get rid of that insulation layer, and move on. But the problem is that if your fluid is not getting that heat that's being released out into the atmosphere now, find out why. Don't just ignore that. You want to look into it further. Okay. A serious problem becomes if you don't monitor that, and all of a sudden now you just have your fluid operating set point might be at, let's say, 500 degrees Fahrenheit, but now all of a sudden 2 years down the road, the fluid's coming out at 490 even though it's set at 500. Most operators' initial reaction is going to be just increase the temperature to 510 so that the fluid comes out at 500. Problem with that is you don't know why that fluid decreased. You never questioned it. It's likely due to degradation. And when you increase that 10 degrees to get a better output, you've just doubled the rate of that degradation from happening. So now you're just prolonging the problem. You're creating a continuous downward spiral of degradation where you could have that catastrophic failure and crack your heater tubes. So it's important to keep note of those things. Changes in your regular steady state operation are important and should be noted, should be reported, should be investigated. Periodically record your readings. Monitor and report any changes. When you get your fluid analysis done, you should be able to report those changes to whoever's doing the analysis. That can go hand in hand with the condition and really make it a lot easier to troubleshoot the problems that you might be having, to make the fluid analysis results and the degradation make a lot more sense both to you and to whoever's doing the analysis. Know what the signs of degradation are. It could be cold points in your system. So you have 3 tanks in series, and all of a sudden tank 2 is not getting the temperature that it needs to, likely due to a blockage in the line due to degradation. You're seeing decreased efficiency. You can take a look at your fluid sample and understand that degradation is typically happening when your fluid has high carbon particulates in it. You see a lot of solids built up into it, soot buildup. Not only that, but the fluid itself is starting to have a much higher viscosity. It's sticking to the walls of whatever your sample container are. So color doesn't really mean as much as the solid buildup, particulate buildup, higher viscosity of the fluid, things that aren't normal according to this visual example. So you want to make sure you know what these degradation signs are in both your operation and in the physical attributes of your fluid. And at the end of the day, let a professional analyze it and give you recommendations based on those results. So that brings us to a deeper look. We just talked about what signs to recognize when you're talking about degradation. Well, the only way to really know what's going on is to take a deeper look. So that brings us to thermal fluid hack number 7, a deeper look. And that really is just the fluid analysis program. One of the things we can recommend the highest, beyond and above all things, is making sure that you have a proper fluid analysis program. Because you can follow every single one of these hacks. You can follow every piece of advice that your supplier gives you, that your equipment manufacturer gives you, that the maintenance guy that's been there for 40 years gives you, and you still don't really know what's going on unless you have your fluid analyzed. It should be initiated and managed, if possible, by your fluid supplier, at least discussed with them and reviewed. Fluid analysis is the most reliable tool for keeping your system running at optimum levels and avoiding unexpected problems. Minimum once a year, annually, as a minimum preventive maintenance practice is what we recommend for a fluid analysis program. Because really what these programs are telling you is they're looking at trends. How did the fluid change from one test to the next? We want to know what happened within that time period. So if you wait for more than a year to do it, there's way too many random mistakes and turnover of people or anything else that could become a serious gap in the knowledge of what happened in that time period between analysis. So once a year is a minimum. Should be specific to heat transfer fluid. You should not just be sending off your thermal fluid or your heat transfer fluid along with your lube oil analysis. Even if you see the tests might be similar, the results are different. The inherent properties mean something different with lubricating oils than they do to heat transfer fluids. You want to make sure you're actually getting a heat transfer fluid analysis. That should include a full report fluid condition, expert recommendations, key point, and a verbal review of the results and best practices for controlling any degradation that might be going on. Basically, the report should come along with a plan of action based on what the results were. Critical tasks of the fluid analysis, and here's where the hack comes in, because you should be looking for at least these as a bare minimum, and honestly, they'll probably be able to get just good enough information on a regular standard analysis just from these three tests. Look at the total acid number, the TAN. That'll show the current level of oxidation on your fluid. And oxidation is the most common way that fluids degrade by a large margin. So being able to test for that total acid number will give you a good indication of whether the fluid's being oxidized. If we find that the fluid's being oxidized and we find that since your last analysis that oxidation level has gone up significantly, we can start to pinpoint and look and troubleshoot for areas that or maintenance practices that we know from experience create oxidation issues. And maybe we can pinpoint that, change your maintenance operations, have somebody turn a valve that wasn't supposed to be turned off when it was turned on before, and really save you a lot of time and headache over the long run. Kinematic viscosity. You've heard me mention kinematic viscosity in multiple of the hacks today. Viscosity is important because it's directly related to fluid efficiency and fluid flow. So that determines whether the fluid has become too viscous or resisting movement or flow to be able to allow for efficient heat transfer. If that's changed too much from the design specs, then we need to take action on that and find out why. Usually if it's thinned out and gotten less viscous, it's indication that the fluid's been cracked or overheated. So that's something to look at. And then you have your distillation range. That can either be through vacuum distillation or most commonly these days is through simulated distillation by gas chromatograph. What that does is it analyzes the actual fluid composition, the high boilers and the low boilers, that can show signs that the fluid's been altered by overheating or oxidizing the fluid itself. So with that and the time that we're looking at, to leave some time for any potential questions, let's move on to the quick hitters. And this is basically meant to just be a review of some of the more important hacks that we've looked at. Just a quick at-a-glance review. When you're charging a system, please make sure you're selecting the proper fluid, not just a fluid that has a maximum temperature rating of 500 when you're operating at 490. You want to make sure that you can have a discussion based on thermal stability, heat transfer efficiency, and the product purity that's going to give you a good, efficient fluid that's going to last you time to get you your investment back, to give you a solid operation that's making your plant money and keeping your people safe. Always avoid filling from the top down. If you need to prime your system, do so with a transfer pump at the low end. By filling from the top down, you're going to be pushing any contaminants that are settled in the expansion tank back into the system, any moisture, and certainly pushing air back down to the system. It's going to create startup nightmares. So when you charge the system, open all high point vents until the fluid reaches them, and that will help push the air out of the system and give you a smoother startup. If you do have water, and you will, start the system up slowly to avoid flashing steam. This is a safety risk. It's an operating situation. Allow the moisture to vent from the expansion tank. Once that moisture is all steamed off from the expansion tank, and you can tell that because it stops showing steam from the vent, you can then start to increase the temperatures at a safer rate to avoid violent discharge of hot oil due to steam expansion. Key point, close the warm-up valve. Whenever you remove water from the system, there is likely to be a valve at a drop-down rate going to the expansion tank that allows you to divert flow of hot fluid up into the tank. This is so the fluid doesn't condense back down into the tank. Key point, this often gets overlooked when that procedure is done and nobody closes that valve down. So when you go to normal operating temperatures, you're oxidizing the fluid at a very high rate. So when you go through the water removal process, remember, these are meant to be hacks, not in detailed procedures, but I'm trying to give you key points. And the key point behind boiling your water off, make sure you close that warm-up valve, that boil-out valve, whatever you might call it, whatever terminology you use. The valve that allows the hot fluid to be actually diverted directly into the tank, after a boil-out procedure, close that valve during normal operation. Otherwise, you will degrade your fluid very rapidly. Other ways to prevent rapid degradation. Never operate above your maximum operating temps. and that includes when your fluid or your system kicks into high fire. You want to make sure that you have a cushion between whatever the maximum operating temperature of your system is and the recommended maximum operating temperature of your fluid. Monitor flows and pressures. Know what your system should be doing. Know what the flow should be. Know what the pressure rate should be. Any valves or any gauges that you have should be read, monitored, reported, and any changes that you see should not be ignored and should not just be adjusted blindly. You should look to find out why that happened, because most commonly it's an area for a red flag for degradation. Again, never operate with the boil out or warm up valve open. Always follow those proper startup and shutdown tips that I gave you earlier. That's going to save you a lot of headaches down the road for degradation issues. And again, we're going to emphasize this one more time. Get your fluid analysis done at least annually. After any change would be important as well. So if you add new fluid, you make an equipment change, and then if you're just experiencing issues, it's important to have a fluid analysis at least discussed as an option. So with that, you can find more fluid hacks and ideas and tips at the Paratherm website on our tip sheet section. That's a lot of information from these, actually just consolidated from those tip sheets. You can subscribe to them. It's some really great periodic information that you can get, some insider tips written in pretty plain English for those that might be new with operating these systems. So it's a great resource. And at this point, we'll open it up for any questions we might have. Thank you very much.
Great, thanks, Ryan. And I'd like to encourage all of the audience, if you do have any questions for Ryan, please submit them now. If we don't have time to get them to them today, we'll have someone follow up with you shortly. So Ryan, our first question, what needs to be considered if changing from a water-based fluid to a hot oil?
Okay, so really one of the key points behind that is a few things. One, why the change? Usually when you have a water-based system, the temperatures that you're operating with are inherently designed for water-based fluids. Those fluids are usually going to be limited by a high temperature range of the boiling point of water or just slightly beyond that. So if you're changing from a water-based system to a hydrocarbon-based heat transfer fluid, I want to know why, because you're usually not going to get the efficiency that you had with water. If there's a reason, then we'll be happy to go through the change-out procedure with you. But I just want to make sure that, we always want to make sure that you understand water is a very efficient product at the temperature range that it's within. If you have a process that needs to go beyond that, or you have a water-sensitive process, or you're just tired of dealing with the pH balances and anything else that come along with water and glycol, that's a different story. If you do decide to move on and switch from a water-based system, there's a lot of equipment considerations and materials of construction compatibility situations that need to come into play. Because compatibility of water glycol or water brine systems, the elements that are going to be compatible with those chemistries are often not going to be the same compatibility criteria that you have with the hydrocarbon-based fluids. So we want to make sure that we have a very thorough analysis of your materials of construction to be sure that you can handle that. And the next case would be your pump, because pump sizing is going to probably be a big issue as well. So making sure that you have a pump that's going to be able to handle the change in viscosity that's going to come along, the change in density that's going to come along with switching to a hydrocarbon-based fluid. Beyond that, if you're going to be retrofitting existing equipment, we talked about this before, you want to make sure, obviously, you had a water-based fluid in there before, you have a very thorough removal of that water, and a very good plan for what to do on startup to boil the water out that might be existing when you put the new hydrocarbon-based thermal fluid in.
Okay. And our next question, what is the average life expectancy for a legitimate heat transfer fluid?
It's a very common question that we get, to which there is no really solid answer for. It really depends on the operating characteristics of the actual operation that they're in, and each one is unique. Over the course of time, if you're just topping a system off here and there due to maybe maintenance leaks or any other reasons why the volume might go down in the fluid, that could replenish the system. It really depends. If you're operating at a temperature that's very close to the recommended operating temperature of the oil itself, that will really cut the life of the fluid down itself. And remember, these degradation mechanisms, the way these fluids break down, follow that Arrhenius equation, which, without getting too fancy, every 18 degrees Fahrenheit rise in temperature will cut the life of the fluid in half because it's going to double the rate of reaction for the degradation happening. So just understand that if you're operating within 50 to 25 degrees of what the maximal operating temperature is, you're cutting that life of the fluid down extremely quickly. So to give you just a solid answer, there really is no irresponsible just to make one up. But I would say based on experience, if you're not getting a solid 5 years at least out of your fluid, then you probably need to make some changes to either the fluid or the operating characteristics that you have. So I'd say 5 years minimum, and that might include some top off here and there. But if you're not getting at least 5 years out of your fluid, then you really should take some action to find out why. But we've had system users that are out there 20 plus years with the initial charge in there. So again, there's too many factors to give a solid answer responsibly, but get the fluid analysis done, follow the tips and tricks, and you'll really extend the life of the fluid out.
Great. Okay. And our next question, what are other reasons for pump cavitation besides water in the system?
It could be a few different things. It could be due to improper volume of the fluid in your system. You may not have the right volume in there, and that's creating air pockets. That's one. Another could be that you are severely have cracked the fluid to where you've created low boilers to the point of vapor pockets being formed. That's another. Another issue could be that you've contaminated the system with a fluid such as a hydraulic fluid or some kind of another multi-purpose fluid or plant industrial type product that has a different, it's not compatible, it's not miscible with your existing fluid. So that because the fluids are not mixing together, you're going to have a formation of, there'll be bubble formation, there'll be vapor pockets. The fluid could be, one fluid could be boiling off inside of the other. Bottom line is, if you are experiencing pump cavitation, it's a problem that needs to be addressed, not just because you're getting operating headaches, but because something's going on that's going to be detrimental to the fluid over time.
Great. Okay. And it looks like this may be our last question. How often should I be topping off with new thermal fluid?
The answer to that one would be you should be focusing more on a fluid analysis program rather than a 100% automatic, I'm going to top fluid off this year. Obviously, if you have a low volume or a low flow situation and you need to top off due to that, then by all means, that's an important procedure. But I've never been a huge fan of, unless the trends and the history of the system call for it, I'm not one to really subscribe to, our procedure's never really been to subscribe to every year top off 20 or 30% just as an automatic maintenance practice. Most of the time that's overkill. And I think that if you are degrading the fluid to the point where you need to do that, you're doing more damage to the new fluid you topped off with than you're doing good with that fluid to the old original charge. So you're actually hurting the new fluid more than you're helping the old fluid by doing that. So I would say don't subscribe to a typical yearly regular top-off situation. Subscribe to the fluid analysis, and if that tells you should top off to maybe serve as a short-term crutch, then use that procedure for that.
Okay. All right. Well, we're going to go ahead and wrap up the question and answer session right there. Thank you to all of our audience members for joining us, and have a great rest of your day.